Okay, so the next little bit here, we're basically going to wrap up the section on E1 eliminations. And truth be told, these are probably a whole lot less interesting than the E2 elimination. So as we said before, let's do an example here. Let's pretend that we've got this. We're going to react this with, say, ethanol. We'll put this in ethanol. Okay, so remember the rate of an E1 elimination is dependent upon some rate constant times the concentration of your alkyl halide. The base isn't in the rate determining step because the first step is the leaving group leaving. So if you're ever trying to do an E1 elimination reaction specifically opposed to an E2, one of the ways that you could go about doing this is reducing the concentration of your base by a lot. So you would use a dilute concentration of your ethoxide. So you're still using a protic solvent, and the same rules applies. If you're using ethoxide, you'd use ethanol as your solvent. But if you wanted to promote E1 over E2, you would dilute your base. So if you ever see on a test dilute whatever, this is going to be a highlight to mean that what I'm getting at is E1. So just keep that in mind. So, and then our final product over here would look like this: CH2, CH3, CH3. Now, if we wanted to do the mechanism of this, of course, the first step is that the leaving group takes its electrons and leaves. Rate determining step. And we've got our carbocation here. In this case, this is a tertiary carbocation. I'll put two H's down here. H. And I've drawn it specifically like this so we could see that one of the reasons why, so we will have all of these various carbons, protons next door, hyperconjugating to stabilize this positive charge. Then our base will come along eventually and grab that proton. Erase this. Electrons go there, and then that forms our final product. Now, in this case, I had three methyl groups, so there is no CH2, CH3. But typically for E1 eliminations, the major product is the Zetziev, Zetsiev's product. Because the second, if we're looking at our energy diagram, the second step is going to resemble the carbocation, and it's going to be hyperconjugated in a way so that you're going to form the most stable double bond. So what's an example? What would be a good example here? So if we were, like, for example, let's pretend that this is our alkene. And if we set this up with, say, dilute methoxide in methanol, the major product would be this or this. So these are the same, right? Same molecule. And the minor product, of course, would be here. So if we star the carbon with the leaving group, the proton's going to be removed from the carbons next door, which I will circle in orange with. We'll make circles with. So those are the. So two of the, removing it from A or removing it from B, give the same product. So that's A or B, and the minor product would be if it was removed from C over here, because you want to form the most stable double bond. So with each E1 eliminations, the major product is Zetsiev's product. So from a practical sense, and if we just do a little review here, remember our energy diagram is as follows. Free energy, reaction coordinate. You form your carbocation, then you're going to form your alkene. And remember, the carbocation, there's another reaction pathway which is possible, and that would be the formation of, say, an SN1 product. So if your goal is to do an elimination reaction on a tertiary alkyl halide, typically, from just a pure practical sense, you won't try an E1, because you get, with E1s, you get SN1 as a possible side reaction. Typically what would happen is you would do an E2 elimination, and so there is no opportunity for SN1 to take place. So from a practical standpoint, E1 eliminations aren't, they're not as particularly as useful as an E2. So so E1s, remember, you can do them on tertiary alkyl halides and slowly on secondary. But E2, you can do them quickly on primary, secondary, or tertiary. So E2 is good in all conditions, which, what I mean conditions there, I mean by the type of alkyl halide. So E2 is practically a more useful elimination reaction, because there's less, there's not a potential side product in an SN1, and you don't have to dilute your reaction mixture. You could just throw in concentrated amount of base and the reaction will be over quicker. So E2 eliminations tend to be more practical. Now I've got some data which would sort of show this. So in the previous example, if we have, let's say we have tert-butyl chloride, and we heat this up in water ethanol mixture. This would be interesting. Someone's done this. Heat this up at 65 degrees Celsius, and the products that they get are the E1 at, say, 36%, and the SN1 OH at 64%. So this is SN1. So if your goal was to make this substrate here, what would we do? Well, you'll notice that these reaction conditions here, we've got a weak base / nucleophile. So if you want to promote an elimination reaction, what do you want to do? You want to use a stronger base. So if you're going to use a stronger base, why not just use ethoxide and ethanol and increase the concentrations? This is very high, and then start doing E2 eliminations fast. And I believe, let's see, I've got some data on that. So when you do the same reaction at 55 degrees Celsius, ethoxide, ethanol, 55 degrees Celsius, the ratio is essentially 100% E2. And you eliminate the SN1 entirely. So this is what I mean by often an E1 elimination isn't necessarily practical. But there are the rare occasions where you might need to use that. So if you ever see dilute in the scheme, this is me telling you we're trying to set up an E1 elimination. Okay, so now we've got a lot of data here. So we've got SN2 reactions, we've got E2 reactions, we've got SN1 reactions, and we've got E1. And these two, in many ways, go hand in hand because the rate determining step is that carbocation formation, carbocation. And the second step, you can either do a substitution or elimination depending upon the reaction conditions. So I guess the next part to talk about is how to set up a reaction so it specifically does what we want it to do. So there's basically 3 different scenarios for what we want to do. Okay, so the first scenario, and it all depends on the very first thing we want to look at is the first question should always be the type of alkyl halide. Because, as we've said numerous times, for primary, SN2 only. And we're talking about substitution here. Secondary, SN2 or SN1. And for tertiary, SN1 only. E2 is good for all. And E1 will be the same as SN1. So this would be E1, E1. But as I said before, this probably isn't very practical for a secondary alkyl halide. So if we're designing a reaction and we want to do a substitution, we should always use conditions that are going to promote a substitution reaction and retard an elimination reaction. So if you want to do a substitution, what we want to use are good nucleophiles and, said another way, poor bases. Something that isn't going to behave as a base, but it could be an excellent nucleophile. The other thing that we want to do for substitution reactions is use aprotic solvents. And the best being polar aprotic solvents. So things like all of our favorite ones, DMSO, DMF, acetonitrile, THF would be another. It's less polar than the other ones, but it's still a aprotic solvent, THF. These things are all going to promote substitution reactions. And why do they promote substitution reactions compared to polar protic solvents? Remember, protic solvents solvate the nucleophile. So if you're Mr. Nucleophile or Mrs. Nucleophile, if you've got all of these, if you get, and we'll just call this R here, if you're solvated by all of these hydrogen bonds, you've got to shed that solvent sphere before you can attack the nucleus. And so on an energy diagram, a solvated nucleus is lower in energy. Sorry, a solvated nucleophile. And so the activation energy you have to come over is going to be higher. If you are, this is a protic solvent, protic. Whereas if you're in an aprotic solvent, you're way up here. You're higher in energy because you're not solvated as much. You still got the negative charge. So the activation energy is actually is going to be lower. So this would be aprotic. So protic solvents are, because they solvate nucleophiles, it increases this energy barrier for, and we're calling this is a substitution reaction, SN2. Now remember, the elimination reaction diagram looked very similar to this, just an E2 looked very similar to this. So in protic solvents, if you want to do an elimination, you've got So to do a substitution, you want good nucleophiles, so poor bases, and you want aprotic solvents. Conversely, for bases, for elimination reactions, you're going to want to use a good base and a protic solvent. And purely because this is going to slow down the substitution reaction. So, and it works out really good. So for elimination reactions, like, and I'll do a little handout for what's a good, like, remember, we know what a good base is, and we know what a good nucleophile is based upon our acid-base chemistry before. So if you've got like like a alkoxide here, these are ideal for E2 elimination reactions because you can just put them in the corresponding solvent which matches. So if you want to do if you're using ethoxide, you would put this in ethanol. And this is going to promote an E2 elimination reaction because it's going to slow down. If there was a possibility of a substitution reaction, it's going to SN2, it's going to slow it down because of you're increasing the activation energy here, this delta G dagger. So there's yeah, so for primary alkyl halides, the two possible reactions are going to be E2 versus SN2. So for SN2, you want to use a good nucleophile. For E2, you want to use a strong base. If your Lewis base can be both, so what happens if you've got, put something like, technically, methoxide could be both, right? It could be a nucleophile or a base. They more often behave like bases than nucleophiles. But so if you wanted to do an E2, you would use methanol as the solvent. This would promote E2. If you were gonna use methoxide as your nucleophile, if you wanted to use it as a nucleophile, if you wanted to do an SN2, your best choice would be something like DMSO or an aprotic solvent. But if you had something which is just only a nucleophile, it's only going to do a substitution reaction. It's not going to do an elimination reaction. So for example, if you had I- iodide, this is only going to do an SN2 reaction. If you had something like tert-butoxide, sorry, this is only going to do an elimination reaction because it only behaves as a base. Things like with regard to oxygen nucleophiles, sort of a general rule, well, yeah, a general rule is that weaker bases tend to work as nucleophiles more than bases. So both of these, like, so this phenolate or this carboxylate anion, both of these are stabilized by resonance. So the resonance stabilized. And so you can often get species like this to actually behave as nucleophiles. Because that negative charge is stabilized by resonance, of course you would want to use an aprotic solvent. So you would want to use DMSO or DMF, something like that. For secondary alkyl halides, E2, SN2. Again, the first, if it's secondary, if it's a good nucleophile, it is going to be SN2. If it's a good base, it's going to be E2. No choice there. Again, the choice really depends upon if it could be either. And here you would want to use the solvent as your choice. So aprotic solvents favor SN2, protic solvents favor E2. Remember, when we're setting up a reaction, we want it to be as efficient as possible. So if I'm doing a test, I won't work at cross purposes. So for example, let's pretend that we've got, we've got OTOS, and we wanted to do an elimination reaction. We've got really two choices. If we use a large bulky base like tert-butoxide, this is going to give us our Hoffman product. where we'll be removing a proton at the least encumbered spot. If we wanted to do the same reaction, make the other alkene, we would use a smaller base like methoxide and in methanol, and this would allow us to remove a proton on the interior carbon. And so our major product would be this. And this would be Zetsiev product. Now, if we wanted to do a substitution reaction, well, we would use something which is a good nucleophile. So let's pretend we've got potassium cyanide here. And we'll put it in acetonitrile just because. Then this will do an SN2 reaction. And the key point here is we got a good nucleophile. In this case, it's linear, which even is more helpful. So it's going to attack from the opposite side and give us our product. Now, if we wanted to use oxygen as the nucleophile, probably the best choice would be using the carboxylate anion here. Sodium plus. And let's use DMSO as our solvent. Remember, this is a protic. And this will give us inversion as well. So if we wanted to replace the oxygen with an oxygen, I would use this as my nucleophile as opposed to, say, methoxide, because this is a strong, what I've highlighted in green here is a much stronger base, right? Even if I was like using methanol and DMSO wouldn't be my best choice because the methoxide is still a strong base. So I'd use something which is stabilized by resonance. Like this is a far better choice of a nucleophile. I hope that makes sense. So whenever we're doing these types of reactions, we always want to do something which is efficient and it gives us our major product in the highest yield possible. All right, so now in the case of tertiary alkyl halides, we've really only got the E2 is still a possibility. When it comes to substitution reactions, we're really left with SN1. And with SN1, there can always be E1 as well. So in designing a reaction like this, if we wanted to do an elimination reaction, I would just choose a strong base. And then is it bulky? This will give us the Hoffman. If it is small, then it would give us the Zetsiev product. For SN1, we really have to use a good nucleophile. And we also need to use a protic solvent here because the carbocation formation is favored with protic solvents because protic solvents can stabilize that transition state. So really, when we're talking about good nucleophiles, I should actually erase this and say only nucleophiles. So if we wanted to put sulfur on there, we would use SH2. I- would work, I guess. Chloride would work. These are all exceedingly weak bases. Bromide too, I guess. Things that are low on the periodic table. So what's a good example of basically hydrolysis reactions would water, water. Probably need some sort of ethanol in there as well because of the, just for solubility purposes. And so what we saw before when we did this reaction was that, where's my data from before? That when we did this, the product was only 64% SN1, and we still had like 36% E1, right? So one of the, like, if you were doing like if you change the nucleophile to SH2, then we would expect this value to increase and this value to decrease because SH2 is a nucleophile and it's not a base, right? Water can be a nucleophile and a base. I guess the most practical SN1 reaction that we've done before involved this, which you guys did in the lab. So you took this, you reacted it with HCl, and this is an E1 SN1 reaction as well. The first step is you're protonating your OH so it becomes a good leaving group. Now it's a leaving group so it can leave. So it departs. This would be the rate determining step. You've got your carbocation. And you had your chloride from before. And your solvent, of course, is water. And you've got H3O plus in there. No, you don't. And then the chloride is a much better nucleophile than water, so it comes in and attacks. And it's not a base, right? Chloride's not a base. So you would get more SN1 versus E1. So the trick for substitution reactions on tertiary alkyl halides is you're going to need to use a protic solvent, or at least a mixture of a protic solvent and an aprotic solvent, just to help stabilize that transition state. But it's helpful if your Lewis base is a far better nucleophile than it is a base, and that's going to promote the SN1 over the E1. But for tertiary alkyl halides, E2 eliminations happen super quickly. So it's just use a strong base and that'll work. So what we'll do next is I'll give you a little decision matrix where you can analyze what's going on. But let's just do a couple of examples here. So this is my room. So the first thing we should look at, of course, is our alkyl halide. And so first things first, so our alkyl halide, our iodide is bonded to a carbon which has got 1, 2, 3 carbons. So it is tertiary. So tertiary, the possibilities for tertiary are E2, E1, SN1. SN1, good nucleophile. E2, good base. So what do we have here? Oxygen with a negative charge isn't stabilized by resonance. This is a good base. And our solvent, so this, and it's not dilute, so dilution would help E1, so let's cross that off the list. It's a good base. It's a better base than it is a nucleophile for sure. So this is also hampering the SN1, right? And if you look at the conditions for this is a protic solvent, which matches the base. So this is really screaming at us E2. And so this should be an E2 reaction. And then the next decision is this a smaller base or is this a bulky base? So bulky, this would be Hoffman. And so with a Hoffman, it would eliminate on carbon 1. If it's a smaller base, let's make this in a different color. Smaller. This would give us Zetsyev. And this would be 2 or 3. And it's not a bulky base. So our major product should be elimination from those orange circles there. So it would give us, this is our major product. Now, if we wanted to do an SN1 reaction here, what would we do differently? We would use something which is, we want to remember E2, the rate is some rate constant times concentration of Rx plus base times concentration of base. We've got a strong base here. So this is going to promote an E2. What we want to do is just remove this. So we could use propanol, and hopefully this could give us our major product, which would be this. And you would get a little bit of E1 as well. But that's how you would do, and if you wanted to do a substitution reaction to put propanol on there, you would want to use something. You would want to make sure that there was no base there. This isn't a particularly good nucleophile. If you like something which is a good nucleophile, it could be something like this: SH2 in propanol. The only difference now is that our nucleophile, it's going to give us SH, substitute SH there. Okay, let's do another one here. Okay, yeah, let's do it like this. Okay, And let's put some conditions. Let's put, so what are we going to do here? Let's use, what will we use? Let's use this. And our solvent will be DMSO. All right, now, so if we do an analysis on this one, we want to check out our substrates. Our leaving group is on here, and it's attached to 2 carbons. So this is a secondary alkyl halide. So E2, so secondary alkyl halide. So this can be E2 or SN2. Those will be the 2 most popular, the fastest ones. There is a possibility, I suppose, of SN1 and E1. Now, the things that are going to promote an SN2 reaction over an SN1 are also going to promote an SN2 reaction over an E2 in many ways. So E2, remember, this is a product, you want to use a product solvent. SN2, you want to use an aprotic solvent. But the key point is that first thing we're going to look at is the Lewis base. Is it a nucleophile or is it a base? And what do we have in this case? We've got the carboxylate anion. So it is a weak base. And so it's not a bad nucleophile. So in the scheme of the teeter-totter, it's on the side of nucleophile over with regards to base. And the other key part is that the solvent is aprotic. So here, this reaction is more set up to be an SN2. So we would get inversion of stereochemistry at that carbon. And we are going to substitute in our leaving group the OTOS leaves. So this would be our major product. If we were going to do an elimination reaction here, we would change our reaction conditions so that we are using a good base. So methoxide, for example, in methanol. These would be the conditions of an E2 elimination reaction. So a stronger base in a protic solvent. So in this case, let's draw this over here. We can grab a proton from these 2 carbons in purple, and it turns out that they would give the same product. There's no difference between the 2 of them. So I suppose there is a difference, yeah. Plus. Yeah, technically there is now, if I think about it. So you get a 50-50 mixture of the 2 of them. For what you're doing in the class, you need to just draw one of them. That's the important part. There are no substituents, other substituents on this ring here, so we don't need to worry about, like, one of the protons on each one of these carbons in purple is going to be axial. So these would be our 2 elimination products. But you can see that they're each di-substituted double bond, so it's fine. There is no Zetyev or Hoffman elimination products in this. You'd get the same if you use methoxide or if you used tetroxide. You get the same two E2 products. Okay. And if we wanted to do an SN1 reaction here, what would we change? We would just use an exceedingly weak so we wanted to do it. If we wanted to do SN1, we would need to, and let's just say it's water is our nucleophile, H2O. We would make sure that it's basically a hydrolysis reaction. Water is both the solvent and the nucleophile. And so this would give us a mixture of products, OH. So this would proceed with racemization. You might see a little bit of E1 in there, but this would be the major product for this. So we're using near neutral conditions here, right? So just water. If you wanted to make this go a little bit quicker, I guess, sulfur would be a good nucleophile here, which would promote an SN1. But then you need to, if that only works if you're trying to make a carbon sulfur bond. Anyway. Okay. So I'm going to give you I'm going to hand out a decision matrix with regard to doing an analysis of your substrates. But the first thing you're going to want to look at is, of course, the alkyl halide. Then determine if your Lewis base is a nucleophile or a Bronsted base. And then some decisions might need to be made with regard to the solvent. Is it an aprotic solvent, which will favor a substitution reaction? Is it a protic solvent, which would favor an elimination reaction? But I'll give you this decision matrix. I'll hand that out in a few minutes. Okay? All right.